And so our next speaker is Dr. Clint Richardson. Dr. Richardson, would you like to use that microphone, or do you want to walk around?
No, I'm fine.
Well, you know, it's being...
It's because we're on Zoom. I do need you to use it.
Okay. All right. Well, my name is Clint Richardson, and my partner in crime here is Alfredo Romero. He's an accelerated master's student that will be graduating in May, and we're going to talk about some of his work that he's been doing with me on looking at culverts. So next. Which one? That one? No.
Middle one is laser.
There. So why study the health of culverts? Well, they're an integral part of our transportation system. Any road you go on, you'll probably see a culvert. And they're there to convey the stormwater effectively under that roadway. So when we look at structural and non-structural defects of our culverts over their design life, that failure, probability of failure, let me start over. These defects increase the probability of failure, and they can be anything from benign temporary road closures, it floods, okay, so you can't pass, or catastrophic. Okay, we've got complete collapse of a culvert. It happened in Los Lunas a couple years ago. Okay, and I'd like for you to think about climate change via the magnitude and frequency of our precipitation events related to the design of new culverts and also the effectiveness of our existing culverts to pass that flow. Okay, as we have more intense precipitation events. Okay. Whoop. Come here, help me. What have I got to do here? Okay. There. Okay, here's some examples of structural and non-structural defects. Corrosion, and then here is siltation. Corrosion, that's a structural. Siltation is non-structural, but it does in fact affect the conveyance of our culvert. Here's a box culvert here where we have some significant cracks that could cause a collapse. Here we have physical damage, not going to affect much of the conveyance except at very, very high flows where it might impede that flow. And here's just some of the things that can happen in our roadway if we have structural and non-structural defects. So, I'm going to talk about our camp project here. It was a 4-year project funded by the DOT. It was a joint project with New Mexico Tech and New Mexico State. Here are the PIs and my partners in crime. So we surveyed with the help of about 45 students employed during the summer. Over the 4 years, we surveyed almost 51,000 culverts using a handheld device, GPS device, and a data dictionary. We were looking at basically trying to come up with a base condition assessment of the major 3 types of culverts that are used in the state: reinforced concrete pipe, concrete box, and then corrugated metal. So we come up with some attributes that they wanted to look at. This was put forth by the state. So for each of the culvert types, we had 5 attributes that they selected that they wanted to look at during these internal inspections. So there are 5 in each culvert type, so you can just see there. Part of them are structural. Siltation obviously is non-structural. So DOT came up with a schema code and a training manual for the students. And then based on that schema code and the data that they input from the inspections, we ended up mining that raw data for the material type, the shape, and then for each of the selected surveyed attributes. So here's just an example of what they came up with. So here's what the students were inspecting, trying to make a visual inspection of, oh, that's 30% silted, okay? And then based on that code, we assign a number, a scale for each of those. So we wanted to use a fuzzy analytical hierarchy process, an algorithm. It's a multi-criteria decision-making tool, and we wanted to use some experts to do these pairwise comparisons. So we had 5 attributes, and that requires each expert to do 10 pairwise comparisons. We had our experts from DOT. One was a drainage consultant, and the other was from our neighbor, DOT. So give you an overview of what fuzzy analytical hierarchy deals with. It, again, is a decision-making tool, okay? And it is very flexible in providing the decision maker a preference, okay? And we do that preference with using triangular fuzzy numbers, and I'll show you that here in just a minute. But it achieves a very high level of accuracy and consistency of judgment using these fuzzy numbers in our pairwise comparisons. And again, we can integrate multiple experts into that process. So here is the linguistics using an importance scale, intensity of importance. And here's our judgment. So each expert had to look at these 5 categories here and then make a pairwise comparison of each of the attributes with another attribute. So here's our fuzzy numbers, okay? And then here's our triangular fuzzy interval. You can use triangular, you can use trapezoidal, you can use Gaussian, whatever. You just have to come up with some kind of fuzzy intervals that then, based on the preference of the expert, we can convert that data into a overall judgment and a weight. So here's our triangular scale. We have about a 33% overlap, and the more overlap you have is bad, but you want to have a certain amount of overlap that helps you characterize the uncertainty in your responses. So here's the template that our experts used for pairwise comparison. Again, 5 attributes, there's 10 pairwise comparisons. So here, attribute A, okay, is strongly more important than attribute B by that expert. And then attribute C is highly more important than attribute A. So each person filled out this template. So we took the individual pairwise comparisons and then integrated that into an overall a matrix. And then we used what is known as the eigenvector process to develop relative weights using an eigenvalue. And all that is just taking a eigenvector, multiplying it by our n by n matrix, and you end up with a scalar, and that's your eigenvalue. And that's important. Your eigenvalue here, the maximum, should equal to about the number of attributes if things are good. So our number is 5, so we should have something pretty close to 5. The higher that number is, the more inconsistency you have in your judgment, in your comparisons. And then what we take is that relative weight vector and then normalize it, and that will get us back to a crisp number, and all those numbers will sum to 1. And then we do a consistency check to see if it's okay. So here are the data that we got for the 3 types of culverts. So you can see we have a weighting factor for each, and it sums to 1. And then looking at the consistency, the ratio was always less than 0.1, and our eigenvalue, maximum eigenvalue, was around 5. So everything's pretty good. So here's some of the data, just looking at a few of the culvert IDs and their location, and then looking at the score for each of the attributes. So you can see here this one is 2.7. So we had some problems with silting, corrosion, scour, no problem, heavy damage, and the channel inlet was pretty good. And then here you got one that was perfect all the way across. So just looking at the corrugated metal, because that turns out to be about 79% of the total number of culverts in the state. So looking at a cutoff value as a starting point for maintenance, looking at a phase maintenance. So out of the 51,000, about 33,000 are corrugated metal, and looking at the mean value and one standard deviation, turns out about 17% was above that cutoff. And then if we look further into those 5,000 or so, we see that of the 5,000, 3,000 or so are damaged, 2,400 are corroded, and about 2,000 of those are silted in. Scour didn't turn out to be too much of a problem. That's just a histogram showing you the 17%. So we wanted to do cluster analysis. Okay, take all of our data and then see if we can look at clusters. So we used what is known as a hotspot analysis, which is part of our ArcGIS Pro. And that will give us a statistical view of clusters of bad culverts and clusters of pretty good culverts. So here is a cluster analysis for the corrugated one for all of the 5 attributes. So this is the total rating. And you can see here we have confidence limits here, 90 to 99%. And we're looking for the red because that's the problem area. So we got a big problem area in the northern. Okay, we got a problem here and a problem here. So Santa Crista Mountains, Sacramento Mountains, and here's the Gila. Okay. So we wanted to look at some environmental conditions, maybe with the clustering, to see if there's any kind of relationships. And we focused in on corrosion and siltation. So corrosion, it's caused by precipitation, soil pH, soil resistivity, clay. Okay. Siltation, obviously caused by precipitation, soil erodibility, the extent of vegetation, and then obviously slope or topography. The problem we ran into is all of us databases have really low resolution as far as pixel size. So it's pretty hard to tease out some relationships. But I thought I'd just show you a couple here. This is corrosion with a 10-year, 6-year precipitation depth. The eastern part of the state is more wet, and then up in the Four Corners area you can see it's more drier. But you see the clusters of corrosion are centered around our mountainous regions. Okay? And again, they're wetter. Okay? And so when you have wet conditions, it helps metal corrode. Here's siltation and erodibility factor, the soil erodibility. Couldn't tease out much there. The higher this number, the more erodible the soil is. So the soil texture is a big key to siltation, but still couldn't tease out a whole lot. So the last thing we wanted to do was just see if we can look at the clustering and also the combination of clusters, siltation, corrosion, siltation, damage, corrosion, and so forth. So using, again, a simple Excel approach, we mined the data with if-and statements and looking at where the rating was greater than 2 cutoff. We had about 287 metal culverts having heavy corrosion and heavy damage. That's about 5%. And if we look at siltation, corrosion, and damage, there was about 73 out of that 287 that had excessive siltation. So siltation is a big problem in the state of New Mexico for culvert maintenance. Just give you a little anecdote here. Out in Cattrall County, there was a 10-foot diameter corrugated metal pipe under a Highway 36. You could just barely see through it, about 6 inches of head space. And we had it cleaned out. In 2 years of looking at that, it had about another 3 feet of sediment in it over the 3 years. So here's one of the slides just for corrosion and physical damage. Not going to show you all of them, but here's the 287 that have a combination of corrosion and physical damage. So again, you can see it's clusters up here, clusters up here, clusters here, clusters here. You can see why I don't use these things. So, future work. We're going to reinspect all the culverts and try to update our ratings. We've got a proposal to the state for the next 4 years. That's very important to look at the temporal changes in the base condition, especially corrosion and siltation. We're doing internal surveys starting this summer using robots and videos, and we've got a master's student working on artificial intelligence to evaluate those videos for structural defects. And then hopefully the big picture is that we can come up with some kind of multi-year phased maintenance program for the state based on our data, the rating system, and these internal videos. So hopefully that'll lead to better maintenance of our infrastructure.
Great, thank you so much. Thank you.